Now our topic is equipotential surface. In a equipotential surface, certain things we need to consider. Those things are, if any surface, if it has certain qualities, those are called as equipotent surfaces. So what are those qualities? First of all, we see first quantity. So first, what is a equipotential surface? So you see any surface. Let's suppose if I take any surface here, like this, a surface. So if a charge was right here, so initially the charge was here. So let's suppose this is a charge Q naught, and it is possessed with some kind of a potential charge. So here a potential it will be possessed. So now whenever it brought to the B point here, still the charge is same, but it brought to B point here. So whenever it brought to B point, here the potential potential is here VA and potential here is VB. So what is the potential difference between these 2 points? I can write. So that is a basic quantity. That's a basic first quality I am going to discuss. So that is a VAB is nothing but what can I write here? VA minus VB. Okay. If the potential is same, even though if I am changing it from one point to other point, if the potential remains constant, if potential remains constant or potential remains same on the surface, that surface is called as an equipotential surface. So I am taking that is a condition. VA is equal to VB, which is nothing but V I am taking here. If the potential is same, then what happens here? Potential difference also becomes potential difference here. What happens here? V minus V, it becomes 0. If potential difference becomes 0 on any surface, that surface is called as an equipotential surface. So that is the first condition. What is the second condition? So now you see here I am doing a work because I am bringing this charge from this point to this point, means definitely there is a work done. Some external work I am doing it on. So here this external work is related to the potential difference. So that external work VAB is nothing but what can I write here? VAB is nothing but VAB, potential difference into the charge. What is the charge here? Q naught charge. So here anyhow potential difference becomes 0. Then what happens here from this one, anyhow if potential difference becomes 0, then a total external work done on this surface is also 0. So there is one more statement also I can say. On any surface, if external work in displacement of a particle from one position to the other position, the external work done on it is 0. So you can say, or else one more other manner you can simply say that external work in changing the position of one point charge from one on the surface from one surface to the from on a surface from one point to the other point, then what can I say? If there is a work done, external work done is 0, then also we can say equipotential surface. So in the both condition here, this is also condition for the equipotential surface. This is also condition for equipotential surface. Now we understood that here equipotential difference and work done. Both are, what is this quantity? Both are scalar quantity, and here it is also become 0. Here it is also become 0. But external work done is related to what here? Electrical field. So that we are going to discuss it. So take down the notes. Let's suppose this is your second condition. What is the third condition? You see, third condition and third quality is let's suppose that is the next thing here. So same thing here. Let's suppose a work done in relation with the electric field intensity. Let's suppose it is brought to the other direction with some distance. It is having an electric field. Then electric field dot a small distance it is displaced. The dot product of these two is nothing but your external work done. So now I am doing it for the electric field in terms of electric field here. Now when if I write if I remove this dot product here, what I can write WAB is equal to E bar DL bar cos theta. If in the case since WAB is becoming 0, if external work is becoming 0, then what can I write? This is anyhow become 0. Then 0 is equal to E bar DL cos theta. If here you simple see here 0 divided by anything will be 0. Okay guys, so theta is cos theta is equal to 0. From there theta is equal to 90 degrees. So simply here electric field lines always normal to the surface. So electric field lines normal to the surface means here the electric field lines is, this is your surface, and electric field lines are normal to it like this. They are also normal to it. If electric field lines are normal to the surface, then also it is an equipotential surface, and equipotential surface should have what? Their potential difference should be 0, then external will become 0, and its field lines always becomes a normal to it. Okay, this is a condition you will get. Next, one more condition we have to see, field lines. So field lines interaction, whether the field lines interact or not, that's an important concept now. So this is your third condition. This all three conditions should be possessed for a equipotential surface. So take down the notes. Next important thing is here. So whenever you are taking a notes, please pause the video and you can take the notes. Now one more thing I wanted to see, how the equipotential surface look like. So if I take a plane, and you have already discussed here, if I take a plane like this plane, I told you already field lines are normal to it. If it is equipotential, then field lines are normal to it. If I take a charge, let's suppose this is a Q charge, around this one field lines will be normal to it like this. So in a spherical manner, everywhere it is uniformly distributed, and these are E is normal to the surface. Next, if I take it for a positive charge here, this is important. Now when I take a positive charge here, both are these things are same nature, then definitely their field lines will be interacted. No, they will not interact. Why? You see, from this particular charge, let's suppose this is a Q1, this is a Q2. From this one you will get a field line, and which is actually here bent, it is actually comes towards the surface, and here you will find more circle and more area will be found in this section, and here also you will get a more area this side. I draw one more line also. Why it is like this? Because there is a same nature, the charges will have a repulsion between them. And one more thing, okay, these are the same charges, for the repulsion will happen, then you will get a more area to back side of it. Though whenever these field lines will be oriented in the back of it. But if I take a dipole, dipole in the sense, if I take a two different charges, then what happens? If I take a two different charges here, so let's take two different charges. Let's take this is a dipole, negative and positive. What happens here? Negative and positive charges. Let's see here. These two are what is this? These two are opposite in nature. So the field lines will be oriented towards the opposite nature charge, towards the opposite natured charge. So this will be oriented like this. It will be more here. Here it will be more. Here also it will be more, but it will not interact. Okay. Here it will have a less distance this side. So here in the middle we will have a more area. So what is the basic thing? Why they are not interacted? You see here, the basic point here if they interact, let's suppose if they interact, here we will get a 1 point. So that point from this charge, it should have its electric field this side, its electric field this side. On the same point, two electric field, this is, let's suppose this is from E1, this is from E2. This is not happens. On the same point, two electric field lines we cannot draw. So that is why these field lines never interact to each other. So even in a equipotential surface, this holds good. So four conditions were important for the equipotential surface. Okay. These are the example for the equipotential surface. Thank you all. Subscribe my channel. If you like, comment, share, everything. Thank you.